single particle energies epsilon into 1 by 1 minus z into e to the minus beta epsilon. This is the grand canonical partition function. And you can write down that PV divided by kBT as logarithm of 2 of ZV. This is the relation of grand canonical partition function to thermodynamics. And the average energy, sorry, average number of particles N can be written as Z dou by dou Z of logarithm of Q, which is given by sum over single particle energy levels 1 divided by Z inverse to the beta epsilon minus. So I can also write this as this implies that PV by kBT can be written as minus sum over single particle energy levels logarithm of 1 plus 1 minus Z into e to the minus beta. Okay, so these are our starting expressions, because this is something which we already saw in the last class for bosons. So this is grand canonical partition function for Bose-Einstein statistics, and from there we can get an expression for PV. And notice that between these two equations, okay, so by eliminating the fugacity between these two equations, we get the equation of state. So last time briefly we discussed how to do this. It cannot be exactly done in many cases, so it has to be approximately done. So this is just a procedure how to get equations. Now we are interested in what is called a thermodynamic limit. Okay, so since we are interested in thermodynamic limit, which lets n tends to infinity, v tends to infinity, such that the density, number density, is finite. And normally you can see that V dependence to V comes through epsilon, that is single particle energy level. Single particle energy. For example, as we have seen, for example, for a particle in 3D box of volume V, allowed values of energy, are given by h bar square pi square into n1 square plus n2 square plus n3 square. These are three quantum numbers divided by twice m L square, but L square is basically v to the power 2 by. Okay, so note that epsilon is inversely related to volume. So as a result, both uh, ground state energy as well as the spacing between the levels go to 0 as v tends to. So because of this, we can say that we can say two things. One is epsilon is equal to 0 is the ground state, of single particle energy spectrum. Now the second thing that we can say is that since since in thermodynamic limit energy spacing goes to 0, implies some sums can be converted to integrals to evaluate property. Now this is important because integrals are easier to handle mathematically. So if you can convert these sums into integrals, then you can evaluate properties with ease. But there is this part came for discussion earlier also. So whenever you have, let's say, sum over single particle energy, and then there is some expression here whatever is the expression. Now this has to be converted into an integral. That means this has to be evaluated by integrating with d epsilon. Then you have to use something called a density of states. So let us call that as some A of epsilon. And then same expression, one can write it. So this is how we convert a summation into an integration using the density of states. Okay, so this is what is called density. Now, it is easy to define this. Suppose, let's say that you have certain energy levels in this fashion. So there is energy level. I am drawing them little separate from each other, but they can be very, very close. So let's say that this is some kind of an energy E, and then you have a small window of energy dE. Okay, so the shaded is this. This is d epsilon. Now you can ask a question. Let us define this dn to be number of energy levels or energy states in energy interval or energy range, whatever you call energy range, d epsilon, around epsilon. That is what I'm going to define it as dn. Now you can easily understand that this is equal to, it should be proportional to d epsilon. As you take bigger window, you get more levels. You get smaller window, you get less levels. But then this is also proportional to something which actually can change with energy. Okay, so that is what is called density of states. Like you know that if you take something like hydrogen atom, initially ground state, first excited state, the spacing is more. As n is increasing, the levels become crowded and crowded and crowded. So your A of epsilon will actually increase. That means as you go to same dE, that window is same size. But if you are taking very close to ground state, you will have less number of levels in that window. If you go to a higher value of n, you will have more and more states will be there. So that is what is your density of states. So we have to evaluate this density of states in order to calculate these properties, because these properties we will calculate by converting the sums into integrals. So our first step now is to find out the density of states. Okay, so we have, let's say this is our first step, density of states for a free particle, because we are having an ideal gas, and ideal gas is a collection of free particles. So this is simple. For a free particle, the energy is given by h bar square k square by 2, where h bar square, where k square is basically h bar square by 2m, and k square is You have three quantum numbers: kx square, ky square, plus kz square. Okay, so you notice that in in case space, in case space, each point is a state. In case space, each point is a state. So, if you want to find out how many number of states are there or how many number of points are there, it is better to go to case space and then work out. Since the energy depends only on the magnitude of k, so it is easy to ask this question that if you have in case space, let's say you have a sphere of radius k. Okay, so let us call this a sphere of radius k, and then let's say you have another sphere of radius. This is dk. So, if you want to ask a question that what is dn, that is number of states. So this is proportional to dk, but then it is also proportional to. So let us call this as some g of k into dk. Now I have to find out what this g of k is. Now this g of k is essentially you calculate the volume of this annular region. Okay, so this volume of the annular region, and so that is equal to 4 pi a square into dk. This is the volume. Okay, so if you have so you know that if you have a point in the case space, the volume associated per point. Okay, so volume per, basically it is a case space volume, let me call it k volume, per state is given by 2 pi whole cube divided by E. Basically, it is 2 pi by L. L is the lattice constant, and 2 pi by L the whole cube. Or in other words, you ask number of states per unit A volume is just the reciprocal of this, 3 by 8 pi cube. So this much is the volume, and this is the number of states per unit volume. So you have this expression. So your dn is equal to this, but this is not yet the density of states in terms of the energy. So this is equal to V divided by, so there is a 4 here and pi here, so V divided by 2 pi square into k square into dk. But you know that energy is given by h bar square k square by 2m. So k square is twice m by h bar square into epsilon. And what is dk? So k square is equal to twice m by h bar square into epsilon, or your k is equal to square root of twice m by h bar square into root of epsilon. So dk will be equal to square root of twice m by h bar square into 1 over 2 root e into d epsilon. So if I substitute that one here, I have v by 2 pi square into twice m by h bar square to the power 3 by 2 into epsilon into 1 by 2 root epsilon d epsilon. Okay, so this will give you v divided by 4 pi square into twice m by h bar square to the power 3 by 2 into root epsilon d epsilon. So you could have also written this as whatever I called as a of epsilon into d epsilon. So from there I can read out the density of states a of epsilon is equal to v divided by 4 pi square into twice m by h bar square to the power 3 by 2 square root of it. So this is the density of states of a free particle in 3 dimensions. So I must say that this is density of states in 3. Okay, so I will not look at density of states in other dimensions today, but you can see that this I will leave it as an exercise, useful exercise to do. We did so a of epsilon. So let's call generally in d dimension. A of epsilon is equal to, you will have some constant which will depend on the dimension CD, and then we have twice m by h bar square to the power p by 2, and we will have epsilon and p minus 2 by 2. So this is the general expression. So in 2 dimension, the density of states will be independent of energy. In 1 dimension, it will be epsilon to the power minus half. So this is the general expression, but this is important. So I would recommend that you can try to, at least in 2 dimension and 1 dimension, it is easy to show. So from that you will be able to make a general expression like this. So this is density of states in 3 dimensions. Okay, so we have this expression. Now we are ready to write down our expressions for n in terms of n and PV by kT in terms of this. So first let us look at, so in the second part, we will try to convert to integral. Okay, convert sums to integral. So first let us try to convert this average number of particles. So consider average number of particles, and you know average number of particles is equal to sum over single particle energies 1 divided by z to the minus 1 e to the beta epsilon minus 1, which I would write it as integral. We are starting from 0 to infinity. Okay, integral 0 to infinity d epsilon into, I have this a epsilon, which is given by v divided by 4 pi square into twice m by h bar square to the power 3 by 2 into root e. Okay. This multiplied by z to the minus 1 e to the beta epsilon minus. Okay. So now what happens? So look at this carefully. Look at this expression carefully. The argument what I am going to present here is argument is the following, that what happens to, so as for example t tends to 0, okay, as t tends to 0, we have this fugacity tends to 1. Okay, as t tends to 0, fugacity tends to 1. Now, if you consider ground state, that is epsilon is equal to 0, the ground state, okay, if you consider this, then this term 1 by e to the beta epsilon minus 1 is like 1 over 0. It goes to 1 over 0 because epsilon equal to 0. So this is 1 minus 1. This is 1 over 0. Whereas our root epsilon is also equal to 0. So because of that, what happens? For epsilon is equal to 0, that term we have an indeterminate form. We have something like 0 divided by 0. Okay, so this is a little inconsistency there in mathematics. So what we can do is we will try to write it in the following fashion. We will write, let us rewrite this n, average value of n, to be, suppose if I take epsilon equal to 0, okay, so then I will have that term I will write separately, that is z divided by 1 minus z, plus now I have epsilon greater than 0 and the same term, the summation. Z inverse is the beta epsilon. Okay. Now you can see that the, so you leave this, so this is somewhat like this. So
sir?
Yes.
So why plus 1, sir?
Sorry, minus 1. So this is like saying that this term is the average occupancy of the ground state, and this term is the average occupancy of all the excited states other than the ground state. Okay, so you can say this is average number of bosons in the ground state. And this is average number of particles number of bosons in all the excited. Okay, so this is kind of an interpretation that we can do to these terms. Now notice that this term, that is leaving this term, I can write average in E as sum over epsilon greater than 0 into 1 by Z inverse e to the beta epsilon minus 1. This I can now write it as V by 4 pi square into twice m by h bar square to the power 3 by 2 and integral 0 to infinity e epsilon square root of epsilon to z to the minus 1 e to the beta epsilon. Now I can still keep this limit from 0 to infinity because now this epsilon, the energy level, is every other level other than the ground state. But even if I include however closer energies, this density of states is going to be very small for that, so it will make a negligible contribution. So what I'm trying to say is, if you plot A of epsilon versus epsilon, this is something like this. Right? This is basically square root of epsilon. So very close to energy level, the A of epsilon is very close to 0, and hence, even if I put this limit to be 0, I will not really make much of a contribution for this integral. Now this is the integral that I have to evaluate. So now I can write the integral in the following fashion. So let us say that substitute beta into epsilon to be equal to some x. So this implies x is equal to, epsilon is equal to x by beta, and d epsilon is dx by beta, and root epsilon is root x by beta. So now you can see in terms of this NE is equal to V by 4 pi square into twice m by h bar square to the power 3 by 2, and so I get 1 beta from d epsilon, 1 by root beta from here. So that is equal to 1 over beta to the power 3 by 2, and the limits don't change, dx into x to the power half divided by z inverse e to the x minus 1. Okay, so now you can see that we will be able to define a class of functions called Bose-Einstein functions. Okay, so let us define a class of functions. Which I will call it as G nu of x. Okay, so this G nu of x is defined like this: 1 by gamma of mu integral 0 to infinity x to the mu minus 1 dx divided by z inverse e to the x minus 1. So as you can see that this is a general, for every mu there is a function. So let us define these functions and see whether we can write, it looks like we can write this in terms of these functions. Okay, so for that let us try to write this coefficients at once. Once we should expand them and then see what kind of form they go to. So let us write this average NE, that is the average number of particles in all the excited states, is V divided by 4 pi square. Okay, and then I will write this as twice m to the power 3 by 2. And we know this h bar is h by 2 pi, right? So there is a 2 pi by h to the power 3 by 2. And this is basically ABT to the power 3 by 2. Okay. And then we have this integral 0 to infinity dx x to the power, I will write it in this fashion, 3 by 2 minus 1 divided by z inverse e to the x minus 1. Okay, so now my idea is that see, this is 2 pi to the power 3 by 2, and I have a 2 pi here, and so this is like 2 pi the whole square, correct? Let me write it as 2 pi the whole square. So that will be 3 by 2 minus, or I can write 2 pi. Okay, so let us keep this. So I want to write V into 2 pi m ABT. Okay, 2 pi m kBT. So there is a 2 pi here, kBT here, and m here. So 2 pi m kBT by this is h square, right? Yeah, so that means this is h square and this 2 pi the square. Okay, by h square to the power 3 by 2. Okay. Now what is remaining is I have from here I have taken only m, so there is 2 power 3 by 2 is there, and there is one another 2 pi to the power 3 by 2 is there, and I have 2 pi the whole square. Okay, so that means into this integral, so let me not write it. So this is equal to, but what is this one? This is V divided by lambda cube. This is thermal de Broglie wavelength. So V divided by lambda cube, and 2 power 3 by 2, 2 power 3 by 2, that is 2 power 3, and then I have 2 square, that means there is 2 there, and pi power 3 by 2 by pi square. So if I bring that to the denominator, this will be 2 by root pi. So 2 by root pi into 0 to infinity dx x to the power 3 by 2 minus 1 divided by z inverse e to the x minus 1. Now you see that your gamma of 3 by 2 can be written as half gamma of half. So which is equal to root pi by 2. So this 2 by root pi is like 1 by gamma of 3 by 2. So this expression gives us in terms of the Bose-Einstein functions defined. So Ne is equal to V divided by lambda cube, V divided by lambda cube into G 3 by 2 of. So I am sorry, I must write this as a function of Z because X is anyway getting integrated. So this is a function of the fugacity. So this is the expression. So we have to do this once, but then we will remember. So whenever we are doing problems, we will directly start from here. So n is related to this. So now let me just okay. So we also go back to this expression that PV over KT over KT is equal to sum over epsilon. You have logarithm of with a negative sign, of course, logarithm of 1 minus z e to the minus beta epsilon. Okay, so this can be written as minus integral 0 to infinity. So you have the same density of states 3 by 4 pi square twice m by h bar square to the power 3 by 2 and root of epsilon. So there is a d epsilon, which is density of states, into we have logarithm of 1 minus certain d to the minus beta epsilon. Okay, so I want you to do this. So let me just leave this as an exercise. So first thing is the first thing is do an integration by parts. Integration by parts to this above integral. Okay, where you are going to consider u is equal to root epsilon and rest of the term to be dv. Okay, and dv is equal to logarithm of 1 minus z e to the minus. Sorry, I think you should consider dv is equal to this and u is equal to beta epsilon, and then repeat whatever I have done. So repeat what is done for average n above, and then you will be able to show that P by kBT. Okay, so that the PV by kBT, that we will cancel on both sides. So P by kBT is nothing but 1 by lambda cube into G pi by 2 of. Okay, so this I will leave it for you as an exercise. Okay, so now what we have done is we have managed to write this in terms of some general Bose-Einstein class of functions that we have defined. Now we will try to understand the nature of these functions. Okay, so that will help us to get an idea of what happens for an ideal Bose class. So third is evaluation of evaluation of mu of. Okay, so we have to evaluate this. Now to evaluate this, remember this is an integral, so we have to actually integrate. So the integration is something like this. We have a mu of z is equal to 1 over gamma of mu into integral 0 to infinity dx x to the power mu minus 1 into, so I will write this as e to the power x divided by z minus, that's what it is, right? So I pull this out, that means e to the x by z, that becomes z into e to the minus x, right? E to the minus x. So this can be written as, I'm actually doing some things which are not very difficult, but they are x to the mu minus 1, and I have z into e to the minus x into, I can write it as 1 minus z into e to the minus x to the power minus 1. Okay, so I pull out this factor and then I have this. Now this is something which you can expand in binomial series. So you have an infinite series. So there are infinite series of integrals. Okay, so let us try to look at that one. That is equal to 1 over gamma of mu integral 0 to infinity dx x to the mu minus 1. Then I have this is like 1 plus x squared, like that, right? So that is z into e to the minus x plus z into e to the minus x the square plus z into e to the minus x cube, and so on. There are infinite things. Now the integration is over x, correct? So now I can pull that out and try to write this as, let me write it as 1 over gamma of mu into integral 0 to infinity dx x to the mu minus 1. And what I have in this bracket, I will write it as some r is equal to 1 to infinity z e to the minus x raised to the power. Okay, so that is what is there in the bracket. Now, since summation and integration are on two different indices, I can interchange them. So I can write sum over r is equal to 1 to infinity. Whatever is not depending on x, I will pull that out. That is, I have z to the power r and 1 by gamma of mu into integral 0 to infinity dx x to the mu minus 1 into e to the minus rx. So this integration I have to perform, and this integration is rather straightforward. So to do this integration, let's set r into x as some t, then x becomes t divided by r, and dx is equal to dt by r. So x to the power mu minus 1 becomes t by r to the power mu minus 1. So if I use all this substitution here. I have r is equal to 1 to infinity, z to the power r, and you see I have r to the power mu coming out, because r to the power mu minus 1 from this term and 1 by r from this term, so that will become r to the power mu into 1 by gamma of mu, integral 0 to infinity, limits don't change. I have dt e to the mu minus 1 e to the minus 2. Now if you know the definition of gamma function, this is gamma function, right? So whatever is this integral is gamma of mu. So you can see that this gamma of mu and this integral will cancel. So the Bose-Einstein function I have now evaluated as g nu of z as so that is z plus z square by 2 to the nu plus z cube by 3 to the nu, and so on. There is an infinite series like that. So this is not a closed form expression, but then you can always evaluate to whatever accuracy that you want, as the infinite series expression is available. So I would consider this as reasonable evaluation of this, because we have at least obtained this as a function of in terms of an infinite series. But then let us try to understand the nature of this function. Okay, so the nature of g nu of z, nature of g nu. Okay. Now remember, for bosons, the highest value that mu can take is the ground state energy, and that is equal to 0. So mu actually is equal to 0 is the highest value of mu, which means the highest value of z is plus 1. So for bosons, remember that 0 is less than or equal to z is less than or equal to 1. Or equivalently, we have minus infinity less than mu less than or equal to 0. So this is the range of chemical potential and efficacy. So that means in this range, you notice that so for 0 less than or equal to z less than or equal to 1, notice that g nu of z is a monotonically increasing function. Monotonically increasing function of z. What does that mean? That means if you have some z prime is greater than z, that implies g nu of z prime is greater than g nu of z. And this is true for all, whatever is your nu, this is true. Now this is an important criteria, or this is an important property of this g nu of z, which you can notice. Of course, this is true if z is positive, and for our situation, z is positive. If it is not positive, then all r terms will become a negative sign, and then this monotonically increasing condition will not be satisfied. But since here the fugacity is a positive quantity, this g nu of z is monotonically an increasing function. Okay, so far so good. So we have the nature of this Gini oxide. So once we have this, then we go back to our problem where we have obtained an expression for the average number of particles occupying all the excited states in terms of one of these functions. So let's look at um, analysis of average number of particles in the excited. Okay, so we have average number of particles is equal to V divided by lambda cube into G 3 by 2 of that. Okay. Now, so here is where an important physical result that we will be showing. So please pay attention. So now what I'm trying to say is that so maximum value of Z. Okay, so maximum value of Z is equal to 1. That means we can say that G 3 by 2 of Z is less than G 3 by 2 of 1. Why? Because this is a monotonically increasing function. The maximum value of Z is 1. So G 3 by 2 of Z is less than G 3 by 2. Correct? This much is clear. So what is G 3 by 2 of 1? G 3 by 2 of 1 is, we have already evaluated that, that is equal to 1 plus 1 by 2 to the power 3 by 2 plus 1 by 3 to the power 3 by 2 plus 1 by 4 to the power 3 by 2 and so on. So this is what is called sum over j is equal to 1 to infinity 1 by j to the power 3 by 2. 1 by j to the power 3 by 2. And in mathematics, there is a well-known function of this type. Okay, so we call it we have what is called Riemann zeta function. Riemann zeta function. Riemann is a mathematician. Zeta is so this zeta looks like this. So zeta of alpha is defined as sum over j is equal to 1 to infinity 1 by j to the power alpha. This is called Riemann zeta function. Now, essentially, what is this one? This is basically a Riemann zeta function of argument 3 by 2. And this infinite series will converge. Okay? So we know that this Riemann zeta function of 3 by 2 will converge to a value of 2.612. So this will converge to a value like this. So that what does that mean? That means that whatever is your Z, the average number of particles that occupy all the excited states, okay, cannot exceed, it should be less than or equal to V by lambda cube into zeta of V by 2. So whatever is there on the right hand side here, this serves as an upper bound on the average number of particles of bosons occupying all excited states. Okay, which apparently are which are infinitely many. Okay, so this is kind of an intriguing result of bosons. There are infinitely many states, but they cannot hold infinitely many particles. There is kind of a upper bound on the average number of particles that all the excited states together can hold. Okay, so I do not know if you find it very intriguing, but this is something which is what the case is, or the nature of these bosons. So now you can think of let's say that I have so let's say that I'm so imagine that you are doing an experiment like this. Okay, so let's discuss it as case 1. Okay, suppose let's say we have n particles, so there are n bosons such that n is less than this value, p by lambda cube into zeta of 3 by 2. Okay, then what happens? Nothing much happens. Okay, all the uh, so all states have some occupants, consistent with what we have discussed so far. But what happens? Imagine what happens. What happens if you go on increasing your n? If we add more and more particles, more bosons to the system, such that now this n becomes larger than p by lambda cube into zeta of 3. What happens? Now, the extra particles that we are adding, they cannot be accommodated in the excited states, because excited state occupancy has an upper bound. Okay, so what will happen that all these particles, okay, so that means so this n minus p by lambda cube into zeta of 3 by 2. Okay, so these many particles, they go to ground state, and there is no limit on the ground state occupancy. Ground state. That means ground state, as many of them, how many ever the particles want, they can go to ground state. There is an upper limit only on the excited states. Go to ground state, for which there is no limit. There is only one state, but you can have any number of particles. So there is a macroscopic occupation of the ground state that is possible when your number of particles is larger than the upper limit. The upper limit is what we have derived as v by lambda cube into zeta of v by 2. This is one case. We could also see it in a different way. That is, let's look at case 2. So in this case, let us try to fix our number of particles. Fix n and fix v. Okay, let's fix n and v. Okay, so maybe it is such that n is less than v by lambda cube zeta of v by 2. Okay. Now notice that so now there is no problem. That means all of them are occupied. All the states are occupied. This is like normal occupation. Now notice that this that the upper bound is a function of temperature. It's a function of temperature. Where is the temperature? The temperature is there in this lambda cube. That is, you have V into 2 pi m ABT by h bar square, h square to the power 3 by 2 into zeta of 3 by 2. So this is temperature dependence comes from here. Now, for a given number of particles, the upper bound is such that the number of particles is less than that upper bound. But I can make this upper bound smaller by reducing the temperature. Okay, so the upper bound on average number of excited state of particles can be reduced by decreasing temperature. So what happens is that if you go on decreasing the temperature, so there exists a temperature, okay, for which this n is equal to this. Okay, so I am going on decreasing this. So for some temperature, which I will call it as EC. We have n, the number of particles is equal to V divided by okay, so V, let me write it like this, V times 2 pi m AB BC divided by h square to the power 3 by 2 into zeta of 3 by 2. Okay, so we can revert this relation and then write an expression for TC. So we can write this TC is equal to h square divided by 2 pi m kb into n divided by v into zeta of 3 by 2 to the power 2 by 3. You can write the temperature at which exactly this upper bound is equal to the number of particles. Okay, then it is easy to understand. It is now easy to see for T less than Tc. That means you are further decreasing the temperature beyond this. Then what happens? The number of particles will be much more than the upper bound. So all those additional particles have to now jump to ground state. So that for T less than Tc, there is a macroscopic occupation. Macroscopic occupation of the ground state. So this phenomena is what we call as Bose-Einstein condensation. This is what is called Bose-Einstein condensation. Okay. So this is a kind of a phase transition from ideal Bose gas. So this is a phase transition from ideal Bose gas to Bose-Einstein condensation. So BEC is one of the very interesting state of matter, and there is a lot of this. Even though Einstein had predicted this in 1925, 1924, but it has been experimentally Bose-Einstein condensation was experimentally observed in mid 90s, 95 or so. 2001 Nobel Prize was given for people who experimentally observed Bose-Einstein condensation at very, very low temperatures. For example, for ideal Bose gas, Tc is of the order of nanokelvin temperature. That means it is something like 10 to the minus 9 Kelvin temperature. So at such temperatures, you will see that the ideal Bose gas will become Bose-Einstein. Now, even though this word condensation is used, we have to understand there are important differences. It's not like gas condensing to liquid, because gas condensing to liquid, that is gas condensing to liquid. This happens in real space. This is one thing. And second thing is that this happens because this happens because of intermolecular forces or interatomic intermolecular forces dominate over thermal disorder or over entropy. Let me put it like over entropy. Okay. Now, Bose-Einstein condensation is very unique type of an example where this BEC happens or what is called the origin of this BEC is quantum mechanical, completely quantum mechanical. Essentially, that means that due to wave function error. There are no interactions. So this is essentially because of the wave function overlap. Because even when this transition takes place from ideal Bose gas to Bose-Einstein condensation, it is still an ideal gas. There are no interactions. And the condensation is not in the real space, but it is in the momentum space. What does that mean? That means these are free particles. So your epsilon is equal to h bar square k square by 2m. These are free particle energies. So epsilon is equal to 0. This implies k is equal to 0. So if you imagine that you have a lot of these energy levels like this, and each one of them are also having a particular value of momentum because it's a free particle. So maybe this particle is here, this particle is here, this particle is here, this particle, some other particle is somewhere. Now what happens is that all of them will come to ground state at t less than tc. So this kind of a jumping is not that like if you have a gas filling the entire chamber, when it becomes liquid, then it will settle onto the bottom of the chamber, right? That is how gas liquid condensation takes place. Or it will be settling onto the walls of the container. So like that, there is no physical space condensation. Wherever particles are there, they will be there, but they will simply stop moving, or simply their momentum becomes zero. So this is what is called condensation in the momentum space. So that is what is the difference between this Bose-Einstein condensation and other phase transitions that we are familiar. Okay, so this is the nature of this transition, and you can see that you can ask a question whether this Bose-Einstein condensation is yeah, okay. So we can ask some simple questions like for example, if you, as I told you, that if you consider this density of states for other dimensions, like I told you that I asked you to do it, but let me write it, is equal to some c times d, cd, some constant, and twice m by h bar square to the d by 2. So I am talking about BEC in other dimensions. Okay, in other dimensions. So then we have epsilon to the power d minus 3 by 2. Okay, so now let's look at 2-dimension. Let's look at 2D. So I just want to say that this 2-dimension, this is independent of proportional to epsilon to the power 0. Okay, so I want to argue so your NE, average value of NE. Okay, so I will not write all these constants, but it will be something like 0 to infinity. I don't have epsilon, because epsilon to the power 0. So, but I can write this as epsilon to the power 1 minus 1, and Z inverse e to the beta epsilon minus 1. So you can see that this N of E in this case can be written as some constant into G1 of because this is 1. So G1 of Z. Now G1 of Z is or G1 of 1 is equal to 1 plus 1 by 2 plus 1 by 3 plus 1 by 4, etc. Now this series is divergence, diverges to, however, very slow divergence, but this is nevertheless divergence. Slowly, however. In fact, this is the famous logarithmic divergence. Diverges to infinity. So there exists no value to which this converges. Okay, unlike the case of G 3 by 2 of 1. Now this converges to 2 point whatever 61, or this converges to a value. So this diverges. This diverges means there is no upper limit. There is no upper limit on n. That simply implies that there is no b's into them. Now you can also argue the same thing with one dimension, because if you take 1D, your A1 of epsilon will be proportional to epsilon to the power minus half. Okay. So this simply implies that your average NE is actually equal to some constant into g to the power half into g to the power half of z. So this also diverges. This definitely diverges much faster than the logarithmic divergence, because g half of 1 is 1 plus 1 by 2 to the half plus 1 by 3 to the half, etc. This diverges. Diverges to infinity. In fact, you can say that g mu of 1, okay, converges for mu greater than 1 and diverges for mu less than or equal to. So because of this, there is no Bose-Einstein condensation in 1. And it is easy to understand that if you have some these dimensions I am just discussing, because these dimensions are one can experimentally check. But if you have 4 dimensions, 5 dimensions, Bose-Einstein condensation is possible, because there exists an upper limit, because those for mu greater than 1, they will all converge, and hence there is a possibility of Bose-Einstein condensation at some point. So this is as far as the situation in other dimensions, other than 3 dimensions. So, any questions at this point? Have you understood this one? There is a kind of whatever I have discussed today, it has arguments which are a combination of some maths and some physics. So if there is any question or if you have not understood something, you can ask.
So, one small doubt, like since the Bose-Einstein condensate is not significant in the real space, like only in the momentum space it is considered, right?
No, what I'm trying to say is that suppose let's say that you have, I'm trying to distinguish between gas, liquid. This is also called condensation, right? Gas
Yes,
liquid
sir. Yes, sir.
condensation and Bose-Einstein condensation. So what I'm trying to say is that if you have some kind of a volume and then the gas molecules are there everywhere like this, okay, they are there
Yes,
occupying
sir.
the entire volume. And when the condensation takes place, what happens is all these molecules will be somewhere on the bottom. The liquid will be here. Okay, so
Yes,
this
sir.
is gas and this is liquid. So this is how the gas liquid condensation happens, because this condensation means just grouping together at some small volume, and that happens in the real space. Now in Bose-Einstein condensation, what happens is that so all these particles which are everywhere. Okay. So now I have to say that these guys are moving. This is moving with this momentum. This is moving with this momentum. This is moving with this momentum. This momentum. So there is, that thing is also there for the gas here also, but
Yeah.
it's not very important, because there the dramatic thing that happens is in the real space. Now they are moving like this. Now when Bose-Einstein condensation takes place, what happens is that these particles will be there only. These particles will be there only, but they don't have arrows. That means their momentum has become zero. That means they
Okay.
are not moving. So there is no real space condensation here, but in the momentum space, they all went to zero. Okay, so
Okay.
you still see that the gas as gas only, but now this gas looks as if it is stuck.
Okay.
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 So the momentums will become zero. So you can say this is your ideal Bose gas. Now, interestingly, why does this happen is um, because of the overlap of the wave functions. That is responsible for this kind of a collective behavior. Now, all of these fellows like one system. They just sit there. In this particular case, when it is in the case of ideal Bose gas, they are still different. Each one is moving independently of the other. There may be some correlation, but they are more or less, they have their independent particle status is there. But once Bose-Einstein condensation happens, there is no independent status. All these particles are a part of some many particle wave function.
Okay.
So that is the difference.
So in one dimension and two dimension, this Bose-Einstein condensate is not the. Can you say that reason once more?
I have just given a reason
Yeah.
mathematically
Yeah.
because the reason why there is a Bose-Einstein condensation in 3 dimension is that there exists an upper limit on the occupation number of the excited state, average occupation number of the excited states. And that upper limit is coming because of the convergence of this Bose-Einstein function to a particular value. But in these cases, because of the dependence of the density of states on the energy, you have this different Bose-Einstein function. In this case, average energy is related to G1 of Z. And if you ask G1 of 1, because 1 is greater than all Z, right? So it's a
Yeah.
monotonic increasing function of Z is valid mathematically for this function. So this is diverging, that means there is no upper limit. The upper limit is infinity. That means you go on adding particles, then there is no macroscopic occupancy of the ground state, both in 1D and 2D.
Okay, sir.
Okay. But I think it is an interesting question to ask and think. What does it physically mean?
Yes, sir.
That
Exactly.
is an interesting question to think, and I encourage you to think about it. So, what does that mean physically? And this is another instance where how deeply physics and mathematics are interconnected. Because I just argue from the mathematical property of a function, and that determines the physics. That means the intimate connection between mathematics and physics, as nature obeys, is something which is very very promising and very exciting here. So, of course, this is a good question to ask, and I would encourage you to think about it. We can come back to that question after you sufficiently think about it.
Okay, sir. Thank you.
Excuse me,
Yeah.
sir.
Yeah.
Sir, can you go back to point 2?
Okay. I'm not sure whether my numbers are continuous.
There. Can you explain that t tending to 0, z tends to 1?
Okay. T tending to 0, z tends to 1. So I want you to recall that we had this expression that average number of particles in energy is equal to 1 by to the x minus 1, where x is equal to epsilon minus mu by kb. Correct? This is what we have. Now we try to plot this function as a function of x with average n. I don't even have to write epsilon because average n. Then we notice that x has to be positive. Okay, this argument you remember. If x is negative, then x has to be positive, greater than or equal to 0. Okay, so what happens if x is negative? This implies n becomes negative, which is unphysical because this is average occupancy. So because of that, x has to be positive. So the lowest value of x, okay, so lowest value of x is 0. Okay, and highest value of x can be infinity. Highest value of x is infinity. So we have said that now what happens as x goes to 0, this function will go to infinity, and then it just goes up. So this is the function. Okay, so that means suppose let's say that we have, so suppose if I fix my epsilon, okay, fix epsilon is equal to, let's say, 0, the ground state. Okay, I am interested in this ground state occupancy. Okay, so then my x is equal to minus mu by kb. correct? So what should mu be? If mu is anything which is positive, now let's say we look at what happens if t goes to 0. T goes to 0, this x goes to x should be equal to okay, mu has to be equal to 0 in this case. Okay, so that means mu has to be equal to 0. Why? Because since x is greater than 0, since x has to be greater than or equal to 0, okay, this implies your mu has to be less than or equal to x. Mu has to be less than or equal to mu has to be less than or equal to epsilon. So if epsilon is 0, then mu has to be less than or equal to 0. So the maximum value of mu is equal to 0. And what is our z? Our z is equal to e to the power mu by k. Okay, so you have a situation where maximum value of z is equal to 1 because mu is 0. So it is like minus infinity is less than mu is less than or equal to 0. This directly gets converted to 0 less than or equal to mu, sorry, less than or equal to z less than or equal to 1.
Sir, but mu goes to 0 and t also goes to 0, no, sir. So we have e to the power 0 by 0.
Yeah. The point is that mu does not go to 0. Mu is equal to 0. Okay, mu is see for a fixed which energies occupation we are looking at. So for a fixed energy, mu is equal to 0. Okay, if you say this is equal to 0, then mu is equal to 0. And so as t goes to 0, this is already 0. So 0 divided by some small value will also be 0. Only when t becomes exactly equal to 0, we have that problem. But that is something which we are not interested in. Okay, very close to 0 also, because mu is identically equal to 0, we will have z. Another way to look at it is in the following. So let us say that n0 is the average number of particles in the ground state, let's say, in epsilon equal to 0. So we know that this can be written as, because we had written that by separating this term 1 minus z. So this I can write it as 1 minus z into average n0 is equal to z. Or you can write this z as average n0 divided by average n0 plus 1. Correct? Now you see what happens in the case when BEC. So BEC occurs when t becomes very small. Okay, so that means your average n0 is very large. Okay, average n0 is very large. So I can write this average n0 plus 1 as average n0 because this is very large. So that once again tells you that this z goes to 1. Okay, this is by looking at the average occupation number in the ground state.
Okay, sir.
Any other question?
Hello, sir.
Yeah.
In that Bose-Einstein condensate below the below TC temperature, uh, whatever extra particle we add will become have zero momentum. So it won't more whatever extra particle we add to that system, it won't move.
Actually, I cannot say that because we have no access to any information of individual particles once you add it to the system. Okay, I can only talk in terms of average number. Okay. So suppose if I have an upper limit and if I am adding more particles than this upper limit, so whatever number that we have, total number minus upper limit, will go to the ground state. I will not know which one will go to ground state. That means which one will move, which one will not move. There won't be any way of knowing that information. You understand? So these are like average statements that we are making. The average number of particles that are occupying the ground state will be total number minus the upper limit.
So some of the particle will move.
Some particles will move, definitely. There is going to be a mixed phase. For T less than Tc, there is going to be mixed phase. But what is interesting is that large number of them will not move.
Okay, sir.
Any other question?
Sir, here for this case, for this ideal boson gas, are these particles interacting with each other?
No, this is an ideal gas. So ideal gas particles are just free and non-interacting.
Sir, but in real system, the particle have some particle interact with each other.
Correct.
So then also we got like experimentally scientists have got okay there is some
Yeah.
Bose-Einstein
So essentially what they do in experiment is they try to take a system to be extremely dilute so that there is no interaction among themselves.
Okay, sir.
So they take they take this whatever gas of atoms, they take them to be very dilute that interactions can be neglected. They take them also so dilute that see they have, imagine that you take a gas and then decrease the temperature to nanokelvin. Do you think it is possible to maintain them as a gas? Because normal liquid, condensation, solid, all those things will happen much higher temperature, right?
Yes, sir.
You take any gas that will become liquid becomes solid. Now you have to understand how to avoid this one, because we want to keep this as a gas up to nanokelvin temperature, which is a big challenge, and that is why it took 70-80 years to experimentally realize this one. Now for
Like
that
like they have to choose some substance that will have very low melting point.
you choose anything. Like for example, Bose-Einstein condensation has been achieved in rubidium atoms, in potassium atoms, sodium atoms, lithium atoms, hydrogen atoms, like that. So these all have interactions. We know that this lithium becomes liquid, lithium becomes solid, right? So all these things have to be avoided. So if you want to avoid, you have to understand how this phase transition takes place to start with. Okay, that understanding has to be there. How a gas becomes liquid. Now a gas becomes liquid because you see gas molecules are gas particles are just flying around. Now they have to start agglomerating. They have to start becoming lumps and become liquid. Means there should be something called some nucleation should happen. Then there should be growth of those particles, and that is how it happens. Now people understood that such a kind of thing happens when you have some impurities. Okay, around the impurities there will be some kind of a conglomeration of particles, and that will lead to condensation. I mean the real space condensation. So one has to choose this so pure substance, so pure set of particles that there are no impurities. And second thing is that these particles which are flying around in the gaseous space, they collide with each other. Okay, and normally what happens when two particles come together and collide, they will simply exchange their momentum and go away. They will not stick together. But if there are three particles coming together, then two of them can stick together and third particle can take all the momentum and then go away. Now these two particles then onwards can fly together, then that can become three particles and so on. So three particle collisions is one of the very important criteria to have condensation. So now they have to choose their system so dilute that the probability of three particle collisions is very, very less. So like that they have to keep maintain this gas as gas up to nanokelvin temperature. That is the challenge.
Okay, sir. So one more thing, sir. Like the technique you have applied here, like separating the ground state part and the excited state part. Something similar I have seen in calculation of Green's function for Coulomb potential, but it's different in one sense, but it is similar in one sense that in two dimension, when we are talking about Green's function in two dimensions, similar like this logarithmic series comes. Like suppose we have a system where charge particles are there, and we try to we arrange them in a two-dimensional surface, and try to find this Coulomb potential or the Green function for the Coulomb potential. Like there also comes a logarithmic function, and here also there is a connection of logarithmic function. Are these things are anyway related?
No, I think there is no relation between these two. See, this logarithmic divergence only comes for the two-dimensional case, and that is because we have the density of states dependence on the energy like that. Okay. So I think there is no physical comparison between these two, but many times there are different physical situations which will mathematically use the same kind of technique. That is possible. Okay, but mathematical similarity need not necessarily translate to physical similarity.
Okay, sir. Thank you, sir.
Yeah.
Hello, sir.
Yes.
Sir, can we have in reality? Can we have non-interacting particles?
In reality, see, there are some interactions in reality, but what we are saying is that whenever you are trying to do some experiment, you must also choose your parameters in such a way that the interactions can be neglected. There is no non-interacting system ideally. Right? So if you can interact, for example, every gas can be considered as an ideal gas at high temperature, low density. That is because at high temperature, they are moving so fast, but they don't give enough time for them to talk to each other and interact. And low density, they are so far away from each other, there is no interaction. So the interactions can be neglected, but there is nothing like a non-interacting system. Some interaction will be there because all the interactions are long-range interactions, correct? So it is essentially an approximate notion, but when we do theory, we consider the non-interacting system because that is easy to handle. And then you can also do an experiment with an appropriate choice of conditions.
Okay, then, sir, what I'm thinking is, if in reality we have some systems which are very lessly interacting, then this Bose-Einstein condensation can happen at a higher temperature, right? Tc can be large. Because,
Yes.
So is that possible?
So basically, the idea is why it is not happening at very high temperature, at reasonably high temperature, is you see this this particular system, or this phase transition is not related to interactions at all. Okay, we are starting with non-interacting system, that is fine. But what happens when this Bose condensation happens is that when this overlap of wave functions take place. And this overlap of wave functions, that means, for example, you take an atom. Atom is a bulky system compared to any quantum mechanical systems. And the de Broglie wavelength of the atom is very small. Now you want to increase it such that the de Broglie wavelength becomes of the order of the size of the cell in which you are keeping these atoms. And that requires you to go to lower and lower temperatures. So that is essentially, that is why I said that this transition, the origin of this transition is quantum mechanical. So you want to understand how to get it at a higher temperature, then you should consider smaller and smaller particles. Okay, so some kind of bosons which are very small, small particles. But we don't have such particles, elementary particles like electrons. They are all fermions.
Okay, sir. Sir, another doubt I have is, sir, this chemical potential is a thermodynamic parameter, right? Like pressure, temperature, volume, like that. So, how to physically increase or decrease that? Because we know how to physically increase pressure or decrease pressure. Temperature we also can do. So, how to do that for chemical potential?
So you have to do that by changing the environment only, because chemical potential is the property of the bath with which your system is interacting, such that there is a kind of particles going from outside to inside or inside to outside is controlled, such that at a constant chemical potential you have an average number of particles are fixed. Okay, so it has to be controlled by the environment. For example, if you consider a metal, there are free electrons inside the metal, but those free electrons are not that free that they can just flow out of the metal. Correct?
Yes, sir.
So if I just take the metal and keep it in the environment, the electrons will not flow out on their own. Right? So,
yes.
But there is something called a work function, so you have to give some energy so that it overcomes that barrier and then comes out, right? But
Yes,
now,
sir.
instead of just putting this metal in the open space, suppose if I put that in some other environment, like I can put it in plasma or in some other environment, then uh, there is a different chemical potential that these electrons will see. So it is always changed by changing the path.
Okay, sir. Sir, the particles can exchange between the system and the surrounding. I mean, the
Yeah.
bath and the system, right? So,
Yeah.
sir, in that case, the bath has to be made up of the same kind of particles, right?
Yes.
I mean, otherwise there will be a mix up.
Yeah.
Okay, sir. Yeah.
Okay. So there are no questions. Can you close?
Hello, sir.
Yeah.
Sir, sir, in the previous class, sir, while deriving the, I mean, this partition functions and all, sir, you at first you wrote something called occupation number representation, right? N0 number of particles are, I mean, is entering into
L0.
E. Yes, sir. So like that. Sir, this the energy state E0 is degenerate, right? There can be two states corresponds to that.
State E0.
Yes, sir. E0, E1, E2. So these energy states, I mean, they are degenerate. There can be two independent energy eigenstates corresponds to that.
So when I'm listing them, I'm just listing the kind of individual states. Okay, I'm not considering that degeneracy into account. For example, let's say I have E1 and E2. Okay, but
Yes,
it
sir.
may be possible that E1 and E2 are same. But I'm listing all of them. That's in this picture. I'm listing all of them.
Yeah. So E0, E1, they are equal like this. You are saying?
In
I mean,
some cases, they may be equal if they are degenerate. But I'm listing every one of the energy levels, whether they are degenerate or non-degenerate. But there is also another scheme in which you can keep track of those degeneracies.
oh,
But
so I think.
that's not this representation. Maybe next time I can show that how to do that one. But that is you have to take the degeneracy of each of these energy levels into account and then do something similar to what we do in microcanonical ensemble.
Oh. So because sir in Fermi-Dirac, I mean in Fermi-Dirac statistics, if we take our particles as electron, then since it has spin up, we can have two. I mean, each energy states can be two-fold degenerate, right? So therefore, I asked.
Yeah.
But you finally put that nj can be 0 or 1
Correct.
corresponds
So
to each EJ. Therefore,
that is what I'm saying. So I did not, even if I have spin, I've never said that these energy levels are without spin or anything. No. So I'm
yeah.
considering that with all degeneracy, I take each one level as just one level.
Okay, sir. Yes, sir. Understood.
Okay. So if there are no questions, then I think we'll close.